Okay, so welcome back. And now we're going to start with this example here. Okay, so example 16 says, consider our salesman. Starting in Seattle. So here's our home in Seattle up here. So right here. Sorry about that. So there we are, up in Seattle. Now the nearest neighbor, so we're going to use the nearest neighbor algorithm. So the nearest neighbor is going to be LA, right? So that's $70 to go to from Seattle to LA. So we're going to go there. Okay, and so that's going to be our nearest neighbor. So that's going to be 70, right? So we have $70. Okay, and then we're going to um, then after we use that one, now we're in LA. So we're going to use the cheapest route from LA. And so where's that going to take us? Well, we've got LA to Dallas, we've got LA to Atlanta, we've got LA to Chicago, and the cheapest one is going to be from LA to Chicago, right? So that's going to add $100 to our total cost, right? And then from there, we're going to find out what the cheapest route is. Now, from there, obviously, we're not going to go back to Seattle, so we're not going to be going that route. But we could go to Dallas or we could go to Atlanta from Chicago. And so the cheapest route is going to be to then head to Atlanta for $75. Okay. And then we've got from there, obviously, the only route we have, because we don't want to, again, we don't want to go to back home yet, is to go to Dallas, right? That's our last stop before heading back to Seattle. So that's going to be adding an 85 and um, and then going back home is $120. Okay. And in this case, when we used the nearest neighbor algorithm, it did find the cheapest route. Okay. Um, but remember, it doesn't always. Okay. Now, going back to our first example, the example up here where it gave us the worst one, right? How can we improve? Well, one way to improve it is to repeat the process with a different vertex. Okay, so a different starting point, and see if the result changes, or if the result changes or gets better. So since the nearest neighbor is a quick and easy algorithm to use, it's not a big deal. So we call this the repeated nearest neighbor algorithm, RNNA. Okay, so we do the nearest neighbor algorithm starting at each vertex, and then we choose the circuit that produces the minimum total weight. Okay, so let's try that with our example. Okay, so if we look at our, going back to the example that we did before, if we start with a different vertex, let's say, for example, um, well, A we already did, we've got 26, right? So let's start with a different vertex. Let's start with B. Well, if we start with B, then what we do is we end up going B to A, and then A to D, and then we end up going D to C, and um, yeah, and then from C to A. or excuse me, I'm sorry. We start with B. We go C to B, right? Like that. So that'll work. So if we add those up, we get 26 again. So we got the same. So no change. Okay, so let's start with C, right? If we start with C, what happens? Okay, if we start with C, we go to A, and then we go to B, and then we go to D, and then we go to C. Okay. Now this gave us a weight of hold on, I messed up because I forgot. I didn't see D. I missed D. D is the cheapest route here. So C, A, and then D, and then we go to B because we don't want to go back to C, right? Because we have to go to unvisited vertices. So to D and then to B, and then of course we go back to C. Okay. Now, but notice that in this case here, we ended up getting 25. So we did do a little better. Okay. Now, let's start with D. Okay. If we start with D, then we would go to A, right? And then the next cheapest would be C. Now, in this case here at C, we don't want to go back to D, so we have to go back, so we have to go to B. And then at this point, we go back to D. But notice that this is actually the same circuit that we got from starting with C. We just started with a different vertex, right? So notice here at C, we had CADB, and here we had the same thing. CADB. Okay? We just start with a different vertex, right? Oh, and by the way, this is a typo. This should not be A. It should be B. Or not B, D, I'm sorry. We start with D. Okay, so now we got a slightly better result with a weight of 25, but still not the optimal circuit in this case. Okay, so now notice that although we did find the circuit by starting at vertex C, we could still write the circuit starting with A, right? So we could write the circuit starting with A. Okay, so we could start with A and write it A, C, B, D, A, right? So once we find the circuit, we can name the circuit starting with any one of the vertices as long as we keep the order, okay? All right, so now let's try this one. Okay, so we're going to try this one. Okay, it says find the circuit generated by the nearest neighbor algorithm starting at vertex B. So we're going to start at vertex B, right? So let's start with B. So I'm going to write B here. Okay. Now, at B, we want to find the cheapest route. Obviously, we're not going to go back to B. We're already at B. So we either need to go to A, C, D, E, or F. So we want to choose the cheapest route. So the cheapest route here is going to be 24. Okay, so that means we're going to go from B to E. Okay. Now when we're at E, right? So we're at E. Now where we're going to go? We're going to go to somewhere else, but not B. We're not going to go back to B. So then that's going to be to D. D is the cheapest route. So we're going to go to D. So we want to go from E to D. Okay. Now that we're at D, where do we want to go? Well, D, well, we don't want to go back to E, right? And we don't want to go back to B. So the cheapest among the rest are going to be what? It's going to be A at 12. So we're going to go to A. And now at A, where do we want to go? Well, we want to go to C or F. So of C or F, the cheapest one is C. And then finally from C, we want to go to F, which is going to be 27. Okay, and then obviously we want to go back because if we read this, it says the table below shows the time in milliseconds. It takes to send a packet of data between computers on a network. If data needed to be sent in sequence to each computer, then notification needed to come back to the original computer. So we need to go back to the original computer. We would be solving the traveling salesman problem. Okay, so the computers are labeled A through F for convenience. So these are all milliseconds. I should have explained this before, sorry. But now that we've gone to F, we need to go back to B because it needs to send notification that it's done, right? So we need to go back to B. So F, back to B. Oops. Okay. So if we add up all of these times, right? So let's see what we get. We get 30, 50, 58, 78, 65, 77, 88. I get 138 milliseconds if I add it right. Right, so 34 and 24 is 58. 58 and 27 is 65. 65 and 12 is 77. And then 88 and then 138. All right, so this will equal 138 milliseconds. Okay, now it says find the circuit generated by the repeated NNA. Okay, so this gives us what? Well, let's see here. This gives us 138. Okay, 138. Right? Okay, so let's erase. Okay. This doesn't really do a good job erasing. Okay, so now let's do another one. So let's start with A. Why don't we just start with A? So let's go A to D. And then we're going to go D to E. Right? So go D, E, all right, D to E, and then E. We don't want to go back to D, so the next cheapest one is going to go B. And then B, we don't want to go to D or E. So the next cheapest one is going to be C. And then C, we don't want to go back to D. So it's going to be F. And then finally, we go from F to A. And then back to D. Hold on a second. Do we add up all the right ones here? And then A to D. Oops. So we went from D to E, E to B, B to C, C to F, F to A, and then A to D. Okay, so what do we get with that one? So we get what? We get 43, 60, 70, 70, 81, 101, 105, 146. So we actually went up. So that was worse. Okay. So see what I'm doing here? So basically what we're going to do is we're going to do the same thing, and we're going to try each one of the computers as a starting point and see which one gives it to us. Okay, gives us the best or optimal um, sequence. Okay, so now, while certainly better than the basic NNA, the nearest neighbor algorithm, unfortunately the repeated nearest neighbor algorithm is still greedy and will produce very bad results for some graphs. As an alternative, our next approach will step back and look at the big picture. It will select first the edges that are shortest, and then fill in the gaps. Okay, so it's called the cheapest link algorithm, and this is the way it works, or it's called the shortest edges algorithm. So the cheapest link algorithm works like this. Step one, you select the cheapest unused edge in the graph. So in the entire graph, we choose the edge that is cheapest. Then we repeat step one, adding the cheapest unused edge to the circuit, unless A, adding the edge would create a circuit that doesn't contain all the vertices, or two, adding the edge would give a vertex of degree 3. Okay? If it does either one of those two things, we will not choose that edge, and we'll choose the next edge, the next cheapest edge. And then 3, repeat until a circuit containing all vertices is formed. Okay, so let's look at example 18. So what we're going to do is the first thing that we do is we're looking at the graph that we looked at. We look at the cheapest edge on the graph, which is the 1, right? So the 1 which connects AC. Oops. Or not AC, AD. Right, so that's 1. So we got AC. Okay, now we choose the next cheapest edge, which is going to be AC, right? So I'm just going to choose this one here. So we'll go all the way to AC. So now we got those two, okay? So now the next cheapest edge is AB, but what happens to AB? If we add AB to the circuit, what do we get? We get vertex A has a degree of 3. So we can't do that. So we're not going to add that one. So now after AB, what is the next cheapest edge? That would be DC. Well, if we add DC, we complete the circuit, and not all the vertices, vertex B is excluded, so we can't do that one either. So let's go to the next one. Well, if we add DB, which is the next cheapest one, then we don't have any issues. Okay, so we'll add that one. And now we can go back to C, because now we can complete the circuit, because the next cheapest edge is the last one, which is 13. And there we go. Now we've got the circuit. Okay. So that is using the cheapest link algorithm. So the circuit would be ACBC. No. Not AC. Keep writing down the wrong thing. Not AC. It's A. So our circuit is going to be A. D. Whatever. B. ADB C A is one way to write it. All right. So let's see here. So that's what I went through here. Now, while the cheapest link algorithm overcomes some of the shortcomings of the nearest neighbor algorithm, it is still only a heuristic algorithm and does not guarantee the optimal circuit. Okay, so just keep that in mind. Okay, so now let's look at example 19. It says the author's band derivative work is doing a bar tour in Oregon. The driving distances are shown below. Plan an efficient route for your teacher to visit all the cities and return to the starting location. Use the nearest neighbor algorithm starting at Portland and then use the cheapest link. So we're going to do this two ways. We're going to use the nearest neighbor algorithm, then we're going to do it again, and we're going to use the cheapest link. Okay, so let's look at how we could do this. Okay, well, if we use the nearest neighbor algorithm, we're going to start at Portland, right? So that's what they told us today. So we're going to start at Portland, and so the cheapest route to go, or the nearest neighbor to go, is going to be the one with the smallest, which is going to be 47. Okay. And that's at Salem. And then from Salem, we're going to go to, so let's do P. And Salem. And then Salem, we're going to go Corvallis. That's the cheapest one, the smallest one. So that's going to be Corvallis. And then from Corvallis, the cheapest route to go is Salem, but we already went to Salem. So the next cheapest is going to be 47, which is Eugene. Okay, so 47, that's Eugene. Okay. And then from Eugene, the shortest route is to Corvallis, but we already been there, so we're going to go to the next one, which is Salem, but we've been there too. So after that, the next cheapest one is Newport. Okay, so Newport we haven't been to yet. So that's Newport. And then from Newport, the cheapest route to go would be Corvallis, but again, we've been there. So the next cheapest route is going to be Salem, but we've been there. And then after that, the next cheapest route is Eugene, but we've been there. So the next cheapest one is going to be Portland, but we've been there. And the next cheapest is going to be Seaside. So we're going to go to Seaside. And then from Seaside, what's the next? The cheapest one is going to be Astoria. Okay, Astoria. And then we go to Astoria, and the next cheapest one, or the cheapest one, is Portland. Been there, well, Seaside, but we just came from there. Portland, we've been to. The next one is 136. Salem, we've been to, and then Newport, we've been to, and then Corvallis, we've been to, and then Eugene, we've been to, and then the next one is going to be, well, it's either going to be Crater Lake or Bend, right? So obviously Bend is the cheaper route. So we're going to go to Bend. Hold on, Crater Lake. Yeah, Crater Lake, Bend, and Ashland. Or hold on. Astoria. So we got Ashland was 347. Yeah. So it's either Ashland at this point. We're down to three. So when we're at Astoria, we've got Ashland, Bend, and Crater Lake. So Bend is the cheaper of the three. And so now we're going to go to Bend. Now Bend, we're either going to go to Ashland or Crater Lake. So Ashland is 200, Crater Lake is 277, so it's going to be Ashland. Okay, and then finally, um, from Ashland, we're going to Crater Lake. Which is our last stop. And then, of course, from Crater Lake, we have to go back to where we started from, which is Portland. So to go back to Portland is 344, right? We can't stay, the teacher can't stay in Crater Lake, got to go back home. Okay, so if we add up all of these numbers, what do we get? We get 1, 3, 4, 5, 6, 7, 8, 9, 908, 950, 950, 990, 1030, 1120, 1130, 1170, 1210, 1220, 1228, 33, 40, 44, 45, 52, 59, 66. So it looks like 1266 is the total, if my math is correct. Okay, so now let's do it again, and let's use the cheapest link, right? Okay, so the cheapest link is we're going to use the cheapest of all of them, right? So what is the cheapest one of all of them? Well, we've got 17 here is from Astoria to Seaside. Is there anything cheaper than that? No, there isn't. So let's start with this one here. Okay, so we'll go from Astoria to Seaside. Okay, now we're going to go from Seaside. Now we don't want to go to Astoria, so let's do Seaside here. So SE, right? Seaside. Oh, no, Astoria to Seaside. So that's going to be AS. Okay. Um, and then Seaside, what's the next one besides 17? We want to do the next one, which is going to be 78. Okay, that's going to take us to Portland. And then from Portland, what do we want to do? We want to use, um, oh, hold on a second. We're using the, hold on, not the near, we're using the cheapest link. Hold on. Or actually, hold on. Am I doing it right? Um, Actually, no, I'm sorry. I reverted back to the, okay, so let's try this again. So we're at Astoria. And we're going to Seaside. Okay, now the next cheapest one on the map on this grid is what? 17. So we got 47. Okay, 47. 40. So we've got 40. Anything less than 40? Anything in the 30s? I don't see anything in the 30s. Yeah, 40. So from Salem to Corvallis. Okay, so let's add that one, right? And now the next highest one is going to be 47. Right. Anything less than 47? No. Okay. So we got 47 here and here, which is Eugene to Corvallis. And we've got Salem to Portland. Well, we don't want to use Eugene to Salem because, um, let's see, Salem. Let's see, Eugene. Eugene to Corvallis. Corvallis to Salem. Actually, this will work. And then Salem to Portland. Okay, so that'll actually work. So if we go to Astoria to Seaside, and then we go Seaside, that's still in the air. But then if we go Corvallis to Salem, We have Salem to Portland. Yeah, so we're good so far, I think. And then what do we got? We got the next one is 52, which is Newport to Corvallis. So we don't want to do that one because we've already got one here. Okay, but you can see that this is, when we have a grid, it gets a little bit complicated to do this. Okay, so here it's easier if we set up our circle like this. Okay, because in a grid, it can get a little hard keeping track of which way to go, and are we violating the algorithm in such a way. So if we create a graph, right? So in this case here, we create a graph of our locations, right? All the different locations in a circle. And it'll be helpful to do this so that way we can see when we add the edges, we can see if an edge has more than 3 degrees, or if we get an edge with a vertex with degree 3, or if it creates a circuit. So if it violates one of those two, right? So again, let's start by the shortest edges, right? So we start adding the shortest edges. And so as we add the shortest edges, Seaside to Astoria, right? The 17 miles, Corvallis to Salem, Portland to Salem, Corvallis to Eugene. Those were the ones that we had just found, right? So we did that. Okay, so this is what we had so far. So far, so good. Okay, now, what do we got now? The next shortest edge is from Corvallis to Newport, which is 52 miles, right? And so that's the one we had an issue with, right? So, but adding that edge would give Corvallis degree 3, right? So we can't do that. So then if we continue to the next cheapest one, right? So continuing on, we could skip over any edge pair that contains Salem or Corvallis because we already used them, right? They've already got 2, right? So Salem and Corvallis we can ignore. Anything with Salem or Corvallis we have to ignore. So we look at the cheapest ones that exclude those two. So we get Portland to Seaside, Eugene and Newport, Portland to Astoria, Ashland to Crater Lake. And so these are the ones that we have. Now, we would Portland to Astoria. Let's look at Portland to Astoria. If we do Portland to Astoria, that closes a circuit, right? So that again, we don't want that. So we'll skip that one. So we're not going to use this one. So in this case here, we'll add the other ones, right? We'll add the other cheapest ones, right? So the rest of these we can add. So Portland to Seaside. Right? So we've got it added to the graph. So Portland to Seaside, Eugene to Newport, and Ashland to Crater Lake. So far, this is what we have. All right. So now, so far, so good. Now, what we're going to do is we could ignore, obviously, Corvallis, Salem, and now we can ignore Portland as well, because now that's got two edges. So we can exclude that one. Oh, and we can exclude Eugene too, because Eugene's got 2 as well. Okay. And so These are the ones we can skip. Oops. Well, what's going on? Okay. So we can skip over those. Okay. So now, well, what do we do? Well, we look at the other pairs that that exclude those. So now we look at Newport to Astoria, Newport to Bend, Bend to Ashland. Okay. So now those are the ones we have. Now, Newport to Astoria. If we go Newport to Astoria, look what happens. It closes the circuit now, right? Because if we trace it, look what happens. We go all the way around. It closes the circuit. Okay? So we don't want to do that. So that one's rejected. And so now what we're going to do is we're going to map Newport to Bend and Bend to Ashland. And so now this is what we have. And now look, now we have a circuit. Okay? So the final circuit written to start at Portland is going to be as follows. Portland to Salem to Corvallis, Eugene, Newport, Bend, Ashland, Crater Lake, Astoria, and Seaside, and then back to Portland. Okay? Which then, as we add up those miles, gives us 1,241 miles, which is better than the one we got with the cheapest, with the nearest neighbor, which was 1,266. Okay? All right. Now, the thing is neither of those was the optimal route. The optimal route is 1,069, which would have been this route. Okay, so even though the cheapest link did give us a better route, it didn't give us the shortest route or the best route. All right. Let's stop there and we'll come back and we'll do a try it.